Thank you for coming. Appreciate it. I've been at Microsoft for 25 years, over 25 years. And even before then, I started as an intern in 95, 96 and 97. Worked on a whole bunch of really cool stuff. Even as an intern, the first Sidewinder Freestyle Pro, which is the first gaming device that uses inertial sensing for gesture control, which was neat. So that would kind of, put me on path for a whole bunch of different things. After undergrad, I went to grad school at UW. In UW, I went into bioengineering. So I went from kind of like electronics and computer science to bioengineering. And that kind of helped establish how I think about innovation and trying to solve problems, trying to approach problems from a very multi-interdisciplinary perspective, combining different disciplines together to solve a problem. Which is kind of like the core philosophy of the team that I ended up establishing in Microsoft in 2001, called the Applied Sciences Group. We're one of the oldest kind of hybrid research engineering groups in the company, and we develop a lot of the AI technologies that ship into Windows. We also develop some of the hardware technologies that you see in our Surface devices, as well as the technologies that make it out into the ecosystem. To our OEM partners and such. So like the pen technology, haptic technology, the display technologies that we end up working on as well. Windows Hello was something that we essentially worked on. But the thing that really has taken a lot of focus of our team, and where the biggest part of the team is really focused on artificial intelligence and the evolution of AI and how it's integrated into the fabric of Windows to create novel experiences, and the implication that is required on the hardware to support those experiences. And the implication is essentially the evolution of silicon that you've seen really spearheaded by the Copilot+ PC. There, we developed a new third processor called the neural processing unit that I'll briefly talk about and help you frame. And that's allowed us to run these really valuable, high demanding workloads, but doing it very efficiently with very low latency. And that's really kind of uncovered a whole new era of experiences. And I'm going to briefly frame that to you. That's like a super quick abstract to the talk. As you can see, really, the philosophy is how do we evolve how people use computers through interaction? So if you look at the evolution of computer form factors, there's this pattern that repeats itself over and over again. This pattern is you have a step function increase in compute. Like, we know this well in the computer science field, right? All of a sudden, like somebody comes up with a new processor and it's like it can do more. And with that more allows you to write more software. Well, it turns out, if you think about it, the more software you write, the more higher level that software ends up becoming. It abstracts the inner workings and the functionality of that processor. No longer are we writing to the bare metal. No longer are we worried about registries. No longer are we worried about memory management. We have tools now to essentially do that. And it's because of this compute that allows us to write more complicated software. And this pattern just continues over and over again. And with the ability of writing, hello, come join us. We just started, so you didn't miss anything. No problem. Have a seat. Thank you. So we were just talking about this pattern that happens in the computing industry. A step function increase in compute allows you to write more software, which changes how people use computers, and that allows you to essentially evolve the computing form factor. And in the situation that we're here today, it's really the Copilot+ PC. And in context to today, really, it's about the silicon that I mentioned, the neural processing unit, the evolution of that, the integration with the three processors, even the fourth processor, which is the cloud, plus what we call software 2.0, which is the advent of using machine learning now in pretty much everything we do. And I'll briefly talk about how these are basically the scaling laws that are so quickly changing our entire field. And it's very important to kind of point out. This is really driving the age of intelligence, where because of this compute allows us to do things very fast, fast and efficiently, so you're not burning up your battery life. And that allows us to have these kind of pervasive experiences integrated throughout the operating system and through different applications. Because of this also level of compute that we're seeing and the efficiencies that we're doing in software, we're really starting to see the shift in moving some of the cloud level experiences that were demanded only by the cloud to actually run now locally on your machine, which is really exciting because that enables a whole host of new things for people, managing privacy, latency, power, and even creating more space in the cloud. And I think the important thing for everyone to keep in mind, and you probably heard this at the keynote and build, really agents is really the North Star. You know, agents is now the new unit of interaction for people. It's also the new unit of programming for developers, which is interesting. It's not really about the application as much as it is agents being wrapped around the application. What's crazy is, like, if you think about it, for the past 60 years, how we use the computer really hasn't changed. You know, this is a very famous demo in the United States from 1968. It's called the Mother of All Demos. This is Douglas Engelbart, and he showed these concepts of a mouse and a keyboard functionality all the way back in 1968. And still to this day, this is how people use computers, and this is how people program things. Xerox. It's mouse and Xerox. Xerox-ish, yeah, sort of thing. It's another research center, yeah. Yeah, and then, so I have a little meme that kind of takes over the video here.
What do you do for a living? Oh, I click buttons. I click this button, which gets me to the point where I click these buttons. And then these buttons get me to the point I click this button. And then sometimes I just click this button a lot. And then sometimes I click these buttons a lot. And unfortunately, my body cannot differentiate running a marathon from having to click all the buttons. I will stare at my screen and I will think, I can't do that project. That's so many buttons that I have to click. Like the buttons are endless for this project. And yet in reality, I'm literally just clicking buttons. And I'm exhausted at the end of the day. And I've been reduced to this. I click these buttons so much, they are worn off. Minnesota and New Mexico, you're not getting an abbreviation because I can't find your buttons anymore. Yeah. I'm starting to think that it's my buttons that are being pushed.
She has a wonderful point. And it's really, while this is a funny video, it actually shows the opportunity that's in front of us with the technologies we're developing. In the end of the day, it's really about helping people honestly click less buttons. You know, this is, you mentioned Xerox. Xerox ended up kind of picking up this work. This is originally from SRI, so it's a research center. I think Stanford Research Center for the most part. A separate organization to do that. That started that work, and then Xerox picked it up, and then other people picked it up from there. Yeah, commercial, yeah. And so, well, the point is that, you know, you'll see this, is like, it's like agents will help you essentially manage this problem. And if you actually see like the pattern that's actually also happened over time with this kind of new step function in compute. Remember I talked about like you're able to write more software. Well, that software in some ways, another way of looking at it is abstracts the functionality of the lower layers. And the big thing that we talk about, even what Satya talks about, is that the new opportunity, the new organizing layer is up here. It's around agents and agents helping essentially mediate all the other layers before. In the 60s, it was really writing code specifically and directly to the hardware. And when you loaded a program into the hardware, that's all the machine could do. There was no this notion of multitasking. There was no notion of me taking that code and running it on another computer. It just didn't exist. Then, you know, companies like Microsoft ended up developing and making popular the BIOS, which is, you know, essentially think about it as a layer that sits in between the hardware and a program. And now all of a sudden developers could write to that layer and they could reuse their code across different hardware platforms. That created an entirely new software industry, new industry that didn't exist before. The graphical user interface came in the 80s, which essentially abstracted the idea of concepts in programming that were visual for people to use. Then, of course, you had the internet and apps in the browser, which kind of changed the way where were applications living? Were they in the cloud or on the device? It almost didn't matter. It abstracted that functionality. Then you had the abstraction of services, web-based intermediation. These applications ended up becoming these big service things that were hubs of aggregating functionality and tasks, think like eBay or Amazon as an example. And now where we are today, that's super exciting, is agents. And you can already see the evolution like deep research, operator, 3 agents, all these agents essentially coming into place that in a lot of ways actually help you manage all these layers below to complete experiences. So let's talk a little bit about compute, some things to kind of note. Obviously on the hardware side, I think everyone's familiar with Moore's law. That's a given. So Moore's law continues to essentially influence the silicon and how many transistors we can fit in a certain space and how much compute we can do on the hardware side. And that helps us essentially design faster kind of kernels and blocks. But the other thing that's kind of also helped Moore's law in some ways, or this compute on the hardware side, is what I call domain-specific silicon innovations. And it's a very simple idea. If you can take silicon and design it for the specific task it's for, it can be more optimal. It makes sense, right? Like if you can take a tool and make that tool better at doing a very specific job, it'll do a better job than that, rather than taking a general tool and trying to make that job make the same workload. That's what the neural processing unit is. If you think about it, like the CPU was really designed around multiplying 2 numbers, scalars. The GPU was designed for graphics. It was for vectors. It was 3-dimensional. But the NPU was a multi-dimensional, going beyond that dimension. It was about doing the computation of what we call tensors, arrays of arrays. And that is like everything in a neural processing unit in the hardware is designed to essentially optimize for that computation. And that's where we gain a lot of efficiency, as an example of where, if you can imagine like where it comes from. Now, that's on the hardware side. On the software side, the thing that's really changed our compute is that we turned the entire paradigm on its head. In the past, when we were writing programs, we would say, okay, we would write a very precise spec because we knew what the inputs were, and we had to design a program to meet that spec, hoping to get the output. And then you would have these testers to go around and like, okay, did it do it? Did it do it? Did it do it? No, it didn't. Let me fix the code. Let me fix the code. With machine learning, it changes the entire game. Machine learning is like, I know what I can put in. I know what I want out. Tell me, computer, what program it should be. And it magically gives it to you in some ways. And that's changed the entire game. This entire structure changes the entire game. The processors that go along with this allows us to essentially not only train, but actually run those programs. And as a result, we've seen this first law of AI, which is models have been getting bigger and bigger and bigger. Until we're like, it's too big. We're just like, like, can they really get bigger? And then we're like, no, we can make them smarter. We can make them smarter. And these sort of techniques have really kind of come together, compounded each other. In fact, even Satya talked about it in his keynote, these kind of compounding 3 factors that came together to drive this age of intelligence that now we're seeing such rapid progress in our industry. This is what makes things so exciting. This is like, if you get tired of people saying like how fast things are changing, well, I mean, yeah, things are changing actually pretty fast. To the point where we already have technology that is superseding human abilities across a number of different fields: reading comprehension, language understanding, speech recognition, and so on and so forth. And even just recently, just giving you a pace of the things that are happening, just over the past 6 months, these are some of the most notable punctuated points of evolution that we've had in the machine learning field. O1, which has really introduced the idea of reasoning. DeepSeek, which challenges how we train programs. operator, which gives the computer the ability to click buttons on your behalf. You have deep research, which is kind of like a wonderful representation of an agent that does work for you. And even just recently, in fact, we just announced it, is the Phi-4 reasoning models that we just put out, which are like cutting edge, being able, for their size, to be able to reason locally on your machine, which is amazing. So something that we thought maybe would have taken us a little longer is now happening faster now. Having this level of capability locally on your machine, on the neural processing unit, is absolutely incredible. Just to give you an idea, so this is DeepSeek R1, just to show what a reasoning model kind of does. And just in a high-level abstraction, we learned very early on when we had models that the more tokens you gave a model, the better it could give you an answer. And in fact, like, there's no better way of kind of like getting the wrong answer by making the model not be able to compute, shorten its answer. And so we knew, like, if somehow we were able to feed back more tokens, it was able to converge. Well, in the most highest level sense, that's kind of what reasoning does. Reasoning basically gives the model more excuse to compute, more tokens to essentially think, to converge on an answer. And you can kind of see it, but it's not just random tokens, it's structured. Structured based on some reinforcement learning function or some human feedback to essentially, this is how you should think. And you can kind of see it, the decomposition that actually happens in the thought process. You have the prompt that the user puts in, and then the model is like, oh, thanks for the prompt, let me restate it for you. Then let me decompose it for you. These are all its stages of thought, which is pretty incredible that it goes through. Right? And this is the same for very similar for all reasoning models, which is kind of nice to kind of understand. And then it reconstructs it, considers the assumptions, questions those assumptions, and then finally gives you an answer. This is kind of the stages now. So that's why these reasoning models, they're not just one shot like we used to have. They're kind of an inner loop that they built into themselves so that they can compute and give you a better, more thoughtful answer. To the point that these models are so good that they've saturated the old benchmarks, which were already challenging. So we had to invent entirely new standard of benchmarks that were just insane to think about. So these are real benchmarks that are out there. Humanities Last Exam, which, this is a representative question, which is like, these are like they sent out a survey and they collected like the 2,500 of the hardest questions one can ever imagine, from the best experts in the world, and said that, try to solve this, and like some of these models are actually able to do some of these tasks, which is pretty insane. Multimodal, being able to understand ancient languages, being able to see ancient languages and comprehend it. Giving, this is SweBench, which is like, here's some code, and here's the GitHub repository, fix this bug, and it just does it for you. Even areas like quantum mechanics or reasoning using visual language, pretty amazing stuff. O3 finally hit and basically showed that reasoning models just were able to trounce everything else before it in regards to performance and computation, and this is super, super exciting. And the reason is that when you have this level of performance, this level of model, it allows you to train better, smaller models, distill the capability of the large models down to the smaller ones. When you have better teachers, you get better students. Does it make sense, right? So this reasoning is really driving what we call now the second law of scaling for artificial intelligence. The first law was about models getting bigger. And then we said, let's shift it from them being bigger to them just computing in real time, online, to be smarter. And with Phi-4 reasoning and Phi-4 reasoning plus, which is the new model we just put out, that run on your Copilot Plus PC and then NPU, I've probably noticed, you can see that, especially the dark lines. I just want you to point out, look how good they are relative to O3 Mini, GPT-4o. Mind you, these are big models. Phi-4 reasoning is something that is like 14 billion parameters that run on your Surface device or Copilot Plus PC with a battery. It's very different. Kind of crazy to think about. And look how good they are relative to all the different benchmarks. This is a trend worth paying attention to and will change the game and how people incorporate these novel experiences into their applications, into the services they want to create, into the agents they want to create. That's super exciting. So this is Phi4 reasoning, a quick demo running on the Copilot Plus PC, running on battery, and you can see it's fully loading the neural processing unit over here. So running this sort of model that can deliver cloud-level experiences locally on your device off the network. If you look at all these innovations in compute kind of stacked on top of each other, they really compound each other and it helps understand why we're able to run such complex workloads on your device. The first one is obviously I talked about, the silicon scaling laws, specialized silicon such as neural processing unit. The runtime that's built into Windows that we just announced, AI Foundry and Windows ML, that essentially optimize where the compute load is. The CPU, the GPU, the NPU, and the tools associated with it to compile the model. The compression techniques that we have that I just mentioned, the model architectures, the better teachers, which allow us to essentially design and distill better student models. That entire thing compounds to having a pretty amazing and really exciting offering of intelligence locally on your machine to create these experiences. And that's allowed us to create all these experiences. These are actually 50 NPU models powering dozens of experiences. The result is, really, Windows has been writing more code for the NPU than ever before, and developers are using more NPU code than ever before. That's really exciting. So we've kind of changed the entire industry because of this work. Pretty much every machine that you will buy will have this neural processing unit, and software will be pervasive running on it, and you'll have all these experiences essentially running. That's kind of the thing to kind of note that's evolving quite rapidly in front of us. I'm going to now shift to agents. So before I do, I know I've thrown a lot at you, so if there are any questions, feel free to ask, interrupt anytime. This isn't just a presentation, it can be collaborative. But the next phase is really, now with all this compute, what do you do with it? You know, we were going from command line to graphical user interface to agents. That's the North Star, that's the goal. That is what allows us to essentially utilize all this compute to create these novel experiences. And what are agents? Well, they're actually different. Not every agent's the same as the other. Agents come in really, this is my taxonomy. And my taxonomy is like, there are really three different classes, major classes. The first one is these limited state agents. And the user wouldn't necessarily interact with them. But think of them as like processes that run in the background that do things for you on your behalf or for the behalf of the application. Specialized agents, like I'm going to tell you about the settings agent that we actually just announced. That's an example of a specialized agent. And then the personal agent, which is really like the co-pilot of the worlds that we're essentially offering. This is an agent that's really the first line interface that might even eventually become the agent of agents. It's the agent that you go to help you manage all the other agents. It's the main organizing layer, and it's very exciting that this is the thing that I think will eventually, everything will move to. So, what's comprised in these agents? What are the main building blocks that you should pay attention to? Well, these are the main things. First, memory is super important because memory establishes context. Then the agent really needs to be able to perceive and reason on top of information. Very important skill and ability. And then it has to act on your behalf or act on the program's behalf, be able to do something with it. And then, of course, to me, I put this on the bottom because entitlements, which basically is permission of the agent, is fundamentally important for the agent to even operate. So this is like, think of it as like the ability, the agent to do something, it needs permission to do something first. In memory, I would just want to kind of allude like what we're doing in Windows to kind of elucidate that. You can already see it happening, the concept of memory in the feature recall. In recall, it's the ability to kind of semantically compress the things that you're looking at and putting it in a relational database. and then being able to create an application that allows you to quickly scrub through that history to find things, either visually or using high-level language. Super cool. And then giving those same tools that enabled that experience to the developer so they can do their own kind of knowledge retrieval and semantic compression inside their own application using their own app data. Super cool. So that's some APIs that we just announced. On the perception and reasoning, let me give you some examples. So click to do is a wonderful example of an agent being able to essentially perceive what's on your screen. Taking a multimodal input, understanding that that's a picture, that's text, and this is a block of text, and then anticipating, because of this context, what you may want to do with that piece of information, and then presenting that to you. That shows perception and reasoning really at its best. Accessibility. Let me show you a demo what we used to provide in regards to an experience for someone needing to see the screen better or hear what's on the screen.
Stock performance at level 3. Comparison of 5-year cumulative total return asterisk. Space. Among Microsoft Corporation, the S&P 500 index and the NASDAQ computer
Probably familiar
index.
with this experience.
Stock performance.
It works.
Graphic.
Maybe not that wonderful.
6/19.
Now let me show you when you throw AI into the mix, is how that experience can evolve.
Describe image window. Generating description.
So it's cranking
The
through.
image shows a graph comparing the 5-year cumulative total return of Microsoft, the S&P 500, and NASDAQ computer index from June 2018 to June 2023. The vertical axis goes up to $400, and the horizontal axis marks yearly intervals. Microsoft, Squares,
What
rose
a
steeply,
more
reaching
wonderful experience, right? To be able to high level describe the screen so that the person can go deeper. And of course, like if you think about it, we're trying to describe the screen on a two-dimensional level. You can do the same thing on a three-dimensional level. And so there are techniques and technologies that we're developing, for example, with Phi Multimodal, to enable developers to just take a picture of a three-dimensional world and do the same level of description. Super neat stuff. Then action, like the kind of one of the last steps that an agent needs to do is to be able to actually act on your behalf. I'll give you some examples here. So Operator just launched. This is the ability of an agent to know how to use software on your behalf, use a mouse and keyboard and click buttons for you. And of course, permissions and entitlement security is super important around that. You know, we just launched, my team actually worked on this feature called Copilot Vision and Highlights. This is a feature that just launched, and it shows kind of, and indicates a little bit of like where things are headed when you have a Copilot next to you trying to solve problems or understand what's in front of your screen, how action really comes into place. So here's a cool demo that Nathan
Good
did.
morning, Nathan. Ready to dive into something interesting today? Let me know what's on your mind or how I can help out.
I'm looking to go to this Huskies game later this summer, but I don't know where to sit. Where's a good area with fan energy?
For the best fan energy, I'd say aim for the dog pack section.
But could you point it out to me? Could you highlight it on the screen here?
I've highlighted the dog pack entrance on your screen. That area is known for its lively fan energy.
Awesome.
Enjoy.
That looks perfect. Thank you.
Super neat demo that does that. Domain-specific agents, here is a settings agent, and the settings agent will take a high-level instruction and just do the command for you. It's like, hey, my mouse, I can't see it. Can you help me out? Yeah, no problem. Here, let me make the pointer bigger for you. That's pretty cool. Those are an example of things to essentially come. The entire thing packaged together is what allows us to have, you know, you have better compute as represented by the Copilot plus PC, software that essentially compounds along with that compute that allow you to enable and run higher and higher complicated, higher value software and programs and AI. Allows you to create novel interactions which really lead towards agents and drive the age of reasoning, all together in a small, beautiful package that runs on a battery in your lap, sometimes connected and sometimes it's not. Thank you.